Hi guys, we're down to the last topic for geometric design, which is earthworks. And under this topic, we will be discussing about earthworks definition, cross-section and volume computation, cut and fill, and mass balance. For highways and related items of work, earthwork includes roadway excavations and roadway embankments. All forms of materials excavated and placed in an embankment are considered earthwork, including soil, granular material, rock, shale, and random material. Transportation developments rarely avoid earthwork. The terrain must frequently be modified in order to build a properly functioning road. Geometric design is frequently used to reduce the cost of earthwork movement. Earthwork is expressed in units like volumes or cubic meters in metric system. Increases in such volumes necessitate the purchase of additional trucks or extra runs of the same truck, both of which are costly. As a result, it is critical for engineers to design roadways that require minimal earthworks. Cross-section and volume computation. The volume must be calculated to determine the amount of earthwork to be done on a specific site. Volumes for linear facilities, such as highways, railways, and runways, can be easily calculated by integrating the areas of the cross-sections along the entire length of the corridor. To put it another way, several cross-sections along the corridor can be chosen and an average taken for the entire length. Under the cross-sections and volume computation, we will be discussing area of cross-sections, computing volume using end area method, computing volume using Prismoidal formula, and computing volume using Prismoidal correction formula. And for all of that, I will be giving examples for us to further understand how to compute using these methods. Area of cross-sections. The methods of determining areas include picking or stripping, plane geometry, planimeter, and using coordinates. Plane geometry is the most commonly used method, requires dividing the section into regular shapes such as triangles and trapezoids. Dimensions may be determined by scaling or from field data. Areas are computed from basic geometric formulas. Once the areas of the sections are determined, the volume between two adjacent sections may be computed by using the average end area. Computing volume using average end area method. Using the formula V is equals to A sub 1 plus A sub 2 over 2 multiplied by L, wherein V stands for volume, A sub 1 is the cross-section area of the first side, A sub 2 the cross-section area of the second side, and L represents the length between the two areas. If one end area has value of 0, the earthwork volume can be considered a pyramid, and the correct formula would be V is equals to A multiplied by L over 3. Computing volume using Prismoidal formula. We will be using the formula which is V sub P is equals to L multiplied by the sum of A1 plus 4A sub M plus A sub 2 over 6. V sub P represents volume given by the Prismoidal formula, while L represents the length between the two areas, A sub 1 the cross-section area of the first side, A sub 2 the cross-section area of the second side, and A sub M is the area of plane surface midway between the two cross-sections. Computing volume using Prismoidal correction formula. The formula will be C sub P is equals to L over 12 multiplied by the product of V sub 1 minus V sub 2 and h sub 1 minus h sub 2 wherein C sub P represents the prismoidal correction, L represents the length between the two areas, V sub 1 minus V sub 2 is the difference of the vertical distance of the two sections, which is the area 1 and area 2, and H sub 1 minus H sub 2 is the difference of the horizontal distance of the two sections. To get the volume, or to solve for the volume using the prismoidal correction formula, we will be subtracting the volume taken from the end area volume using the end area method, and we subtract it with a prismoidal correction. Cut and fill. Cut and fill excavation is also known as excavation and embankment. It's a process where excavators move and place volumes of material to create optimal terrain for a road, railway, or canal. Earth that is brought in is referred to as fill, while earth that is removed is referred to as cut. Designers typically create drawings known as cut and fill diagrams, which depict the cut or fill present at any given site. This drawing is nothing more than a graph, with the site location on the x-axis, and fill being the positive range of the y-axis, and cut being the negative range of the x-axis. Mass balance. An overall mass balance can be computed using the cut and fill data. The mass balance represents the total amount of earth left over if positive or needed if negative at a given site based on a design up to that point. It is a useful information because it can determine how much remaining or required earth will be present at the end of a project, allowing designers to calculate how much expense will be incurred to haul out excess dirt or haul in needed additional. Furthermore, a graphic representation of a mass balance diagram can assist designers in moving dirt internally to save money. Similar to the cut and fill diagram, the mass balance diagram is illustrated in two axes. The x-axis embodies site location along the roadway corridor, and the y-axis signifies the amount of earth, either in excess or positive, or needed negative. And now we are down for the example problem to solve for the area of cross-sections and the volume of the earthworks. For problem number 1, we are given the cross-section notes of an earthworks for a proposed extension of NLEX. So station 10 plus 100. At distance 0, we are given a vertical distance of positive 1.5. And at distance 4.5, horizontal distance 4.5, we are given a vertical distance of positive 1.0. And at a horizontal distance 6.45, we are given a vertical distance of positive 2.3. Now we are asked to compute for the side slope S of the section, the width of the road base, and the area of the cross-section. So to solve for the side slope of the section, we are going to use the equation b over 2 plus 2.3s is equals to 6.45, which is the horizontal distance from 0 on the left side. And we have to subtract it by b over 2 plus s is equals to 4.25, which is the horizontal distance from 0 to the right. And solving for s, we obtain 1.3s is equals to 1.95 and divide both sides with 1.3. We get the answer s is equals to 1.5. So for the width of the road base, we use the equation b over 2 plus s, the right side equation. B over 2 plus s is equals to 4.25, and we substitute the value of s, which we get from the first question, which is 1.5. And so we arrive to the answer b is equals to 6. So to solve for the area of the cross section, we use the Cavalier's theorem, since the sections are not perfect triangle. So we multiply 1/2 by the base and the height. For section 1, the base is 3 and the height is 2.3. And for section 2, the base is 1.5 and the height is 6.45. And for section 3, the base is 1.5 and the height of the section is 4.25. And for section 4, the base is 3 and the height is 1. So the area of the cross section is equivalent now to 13.16 square meter. And for the next problem, computing volume using average and area method and prismoidal correction. From the given cross-section of an earthworks between A, position 20 plus 200, and B, position 20 plus 220, assuming both have same slope and width of base. For station A, at distance 0, the vertical we are given a vertical distance of positive 2.0, and at a horizontal distance 4.8, we are given a vertical distance of 1.2, and at a horizontal distance of 6.6, we are given a vertical distance of positive 2.4. For station B, at distance 0, the vertical distance is missing or unknown, and at the horizontal distance 7.2, the vertical distance is positive 2.8, and at the horizontal distance 6.3, the vertical distance is 2.2. We are asked to compute the width of the base, the value of cut at station B if it has an area of 16.82 square meter, and the volume between A and B using the prismoidal correction. So our solution for the computation of the width of the base, we use the equation B over 2 plus 2.8 S, which is equivalent to the horizontal distance 7.2, minus B over 2 plus 2.2 S is equivalent to 6.3, the horizontal distance on the left side. And we arrived at the value of S, which is 1.5. So now to solve for the width of the base, we substitute the value of S, which is 1.5, to the equation B over 2 plus 2.2 multiplied by 1.5S is equals to 6.3. So the width of the base is equals to 6 meters. For the next question, we are asked to solve for the value of the cut at station B, and we are going to use the area of the cross-section. And for station B, the area of the cross-section is 16.82. Now, we equate it with the 4 sections, which is we multiply 1/2 to the base and height of each section. And for section 1, the base is equivalent to 3 and the height is 2.2. For section 2, the base is unknown and we are going to solve for it. And the height is 6.3. For similarly, for section 3, the base is unknown and the height is 7.2. And for section 4, the base is 3 and the height is 2.8. So solving for x, we arrive at the answer of 1.38. X is equivalent to 1.38. For the next question, we are asked to compute the volume using prismoidal correction. So using the cross-section area, for area 1, which is station A, we have to solve for the area 1 since it is not given. So area 1 is equals to 1/2 multiplied by the base and height of the 4 section. I mean, the summation of the base and height of the 4 section. So for section 1, the base is equals to 3 and the height is equivalent to 2.4. For section 2, the base is equivalent to 2 and the height is 6.6. For section 3, the base is 2 and the height is 4.8. And for the last section, the base is equivalent to 3 and the height is 1.2. So solving for the area of area 1, we arrive at the answer of 16.80 square meter. So we now proceed for the end area volume using the value of area 1 and area 2. Now we use the formula end area volume is equivalent to area 1 plus area 2 over 2 multiplied by the length. So area 1 is equals to 16.80 plus the value of area 2, which is 16.82, all over 2 multiplied by the length of the section, which is 20. So the value of the end area volume is equivalent to 336.20 cubic meter. And to solve for the volume using prismoidal correction, we have to solve for the prismoidal correction first. Using the formula L over 12 multiplied by the difference of the vertical vertical distance of the section, and as well as the difference of the horizontal distance of the section. So the length is equivalent to 20 all over 12, and the vertical distance for area 1 is equivalent to 2, and the vertical distance for area 2 is 1.8, and the horizontal distance for area 1 is 11.40, and the horizontal distance for area 2 is 13.5. So we arrive for the value of prismoidal correction equivalent to negative 2.17. And now computing for the volume using prismoidal correction, we substitute the value we get for the end area volume and the prismoidal correction, which is 336.20 minus negative 2.17, and now we arrive to the value of volume, which is equivalent to 338.37 cubic meter. For the last problem, for cut and fill and mass balance, we are given the following cut and fill profile for each meter along 10-meter strip of road built on very hilly terrain. And we are asked to estimate the amount of dirt left over or needed for the project. So for distance 0 meters, we have 3 meters of fill. For distance 1 meter, we have 1 meter of fill. For distance 2 meters, we have 2 meters of cut. For distance 3 meters, we have 5 meters of cut. For distance 4 meters, we have 7 meters of cut. For 5 meters, we have 8 meters of cut. For distance 6 meters, we have 2 meters of cut. For distance 7 meters, we have 1 meter of fill. And for distance 8 meters, we have 3 meters of fill. For distance 9 meters, we have 6 meters of fill. And lastly, for distance 10 meters, we have 7 meters of fill. Now, the solution would be like if cut is considered an excess of available earth and fill is considered a reduction of available earth, the problem becomes one of a simple addition or subtraction. So, like what I've discussed, when we say fill, we use negative sign to represent the fill and positive sign to represent the cut. So we use negative sign for fill since it's a reduction of the available earth, and positive sign for cut since there's an excess available earth. When we gain excess available earth. So the solution would be the summation of all the cut and fill values, making putting negative sign for the fill and positive sign for the cut, and we multiply all of them by 1 square meter. So all in all, our mass balance is equivalent, the amount of dirt left over for the needed project is equivalent to 3 cubic meter.